Hi everyone, welcome to another tutorial on LSED. This will be a two-part video in which we'll cover the basics of statistics as is applicable to us in our daily lives and in business or work. We'll try and cover the most common and relevant parts of this from a beginner's perspective, so this will be a very easy and simple video. And we'll also try and develop an intuitive understanding of the topics at hand. We'll look at the mathematical formulation. We also try and see how would it be calculated in a tool like Excel. So having said that, let's begin. So within the basics of statistics, there are two common areas that you will frequently encounter. These are descriptive and inferential statistics. What do these really mean? You have the formal definitions on the screen. Descriptive statistics, as the word descriptive suggests, is aimed at describing a data set or a set of values in the best possible way, such that one can then derive conclusions or get a concrete idea as to what is the data set like. On the other hand, when we talk about inferential statistics, we may or may not have access to values of all the data points in the data set. In that case, what we try and do is try and obtain a sample using different sampling methods. And then we use different statistical techniques to try and understand what the overall data set might look like or might represent on the basis of that sample. Let's talk a bit more about this. So, for instance, if there's a class, let's say there's a class of students, the class has 40 students. And what we want to find out is we want to understand what is the percentage of students in the class that prefer Coke and what is the percentage of students in the class that prefer Pepsi. And the class has 40 students. Let's assume for simplicity that we can talk to all the students and obtain their preferences. Now, with that assumption, it will be a fairly easy exercise. We can ask all of them, roll out a simple survey, and everybody will mark either Coke or Pepsi, and we will get to understand what is the percentage that likes Coke versus Pepsi. This would be an example of descriptive statistics. Remember that in this case, all of the data points, that is, all the 40 students, we are getting values or information from. In this case, the set of 40 students would be known as the population. So when you can get values or data values from the entire set of data points or the complete group of data points that you're looking at, then that is known as the population. Another example of this is, let's say that we wanted to calculate the height of the students in the class. If we have access to all the 40 students, we can easily measure the height of each of those 40 students, and then we will be able to describe the class, or rather the height of the class. Since we are able to get the data values for everybody in the class, then that is data being gathered on a population. And the use of statistics to describe this information will be an example of descriptive statistics. Now let's take a look at a different sort of example. Let's say somebody wanted to say that in a specific city or in a specific state, what is the percentage of population that likes Coke and what is the percentage of population that likes Pepsi? Now, this will be a difficult exercise. Imagine a city with 1 million inhabitants. It will not be possible for us, even with electronic and digital methods, to accurately get the likes and dislikes of people, of all of those 1 million people. In this case, since we cannot get data values for all of those 1 million people, the only option left to us then will be to resort to indirect methods. So for instance, we can select a small but a relevant sample of people, and then using that sample, we can then derive the percentage of likes and dislikes, or the percentage of likes for Coke and the likes for Pepsi. And then basis those numbers, we can then conclude or draw inferences as to what would those numbers look like for the entire population of the entire city. This would be a typical example or a use case for inferential statistics, where in step one, what you do is you since you do not have access to data for all of the data set, you choose a relevant sample, then you find out the values of that variable for that relevant sample, and then basis that, using statistical methods and techniques, then you can draw conclusions. Where is this useful? So this is useful in multiple places. So inferential statistics would be used wherever, due to logistical issues or otherwise, you cannot gain access to all the data values. The other example of this is where it is cost prohibitive. So for instance, let's say a new car has been launched in the market. It's been 1 year. And now what we want to calculate is what is the capability of that car to withstand accidents. How would something like this be calculated? Can you possibly break or crash every car that has been manufactured? And that phase you'll get data points for the entire set of data values, and then you can calculate the resistance or the capability of the car to withstand an accident. Of course not. You can't do that. It will be extremely expensive and it wouldn't make any sense. In such cases where testing is cost prohibitive, testing is dangerous, or there are logistical issues or data access issues, in those cases, inferential statistics becomes extremely important for us to understand what the nature of a certain variable is for the entire population. Remember, these are just inferences. These are not very concrete values that you can get from descriptive statistics. So that at a layman level or at a beginner's level is the difference between descriptive statistics and inferential statistics. Both of them describe the population. However, in the first case, you have all the data values. In the second case, you don't have all the data values. You get a sample and you measure the sample, and from that, draw conclusions. So now that we have this at the back of our mind, let's take a look at this quick visualization. On the left-hand side, in the blue colored box, you have 9 different data points, and we have access to data values of all the data points. In this case, the 9 data values represent the population. Since we have data values for each and every element of the population, we can resort to descriptive statistics. On the other hand, look at the second box on the right-hand side. Let's say, and this also has 9 data points, but unfortunately, we don't have access to data values for all the 9 data points. We only have access to, let's say, 4 values, as you can see. In this case, if you wanted to draw conclusions, if you wanted to derive conclusions about this population, you can't do it directly. You would have to first take a sample. In this case, our sample is those 4 values, for instance, for which we have access to data. And then we can use statistical methods to apply to these 4 data points. Basis that, we can then predict, forecast, evaluate, draw inferences, conclusions on the entire population. One very important distinction is, remember that whenever we are dealing with a variable, for example, let's say we had to calculate the height. Let's say we had to calculate the height of everybody in a class of 30 students. In this case, and let's say we want to calculate the average height. In this case, the average is going to be calculated in a certain way, but it will be for the entire population. On the other hand, let's say you are asked to calculate the average height of everybody who lives in a city of 1 million inhabitants. In that case, you will do that using a sample, and you will still calculate an average. The difference is, in the first case, that average is generally known as a parameter. And in the second case, when you're using a sample, that same variable will be known as statistic. So the average height in the first scenario will be called a parameter whenever you're dealing with the entire population. On the other hand, the average height when you're dealing with a sample is known as a statistic. Very often you will hear this terminology in terminology when you're dealing with statistical text material, where there'll be description in terms of parameter and statistic. So it's important that we learn to distinguish this very early on. you will often see, and we'll look at an example later on, where the same thing like an average, and a lot of you who are well acquainted with statistical formulas like averages, medians, standard deviation, variance, etc., where or other statistical measures, you will see sometimes they're called parameters and sometimes they're called statistic. So how do you differentiate? Remember, one is when you're describing the entire population, the other is when you're drawing inferences of the population using a sample. All right. So moving on to the next thing. So how are these descriptive, how's the descriptive statistics really done? Or what are the different parameters of statistics that you can expect to see even in statistical inferences theory? So basically there are two different classes of parameters or statistics that you'll encounter. The classes are, you have measures of central tendency and you have measures of dispersion. I'm sure this is not new for almost all of you. But let's quickly recap what we already know about this. So measures of central tendency is the capability to describe a data set by a single index or a single number. And generally this number will be a central point. And generally this number will be a central point. For instance, let's say you've been buying apples for a while. So every month or every week you buy some apples. The price that you will have of the apples over, let's say, the last 6 months will vary. So sometimes it could be some value X, sometimes it could be some value Y. So if somebody asks you what is the price of apple, chances are you will not say X or you will not say Y. You'll probably say a value which lies somewhere in between. So that's what measures of central tendency is. Its objective is to describe the entire data set or the entire group by a single number or a single value. On the other hand, when we look at measures of dispersion, remember that in order to describe a data set, it is not just good enough to be able to point out the central point. It is equally important to be able to describe the width or the distribution or the range of the data set. And these are generally classified as measures of dispersion. So whenever we deal with parameters or we deal with statistics, we will be dealing with measures of central tendency and measures of dispersion. So let's understand this a bit more. So what are the common examples of measures of central tendency and measures of dispersion? So these are the most common ones that you're seeing on the screen. This is by no means an exhaustive list, but these are some of the most common ones and some of the most used ones. So when we talk of measures of central tendency, the first undoubted parameter statistic that you'll encounter is the mean. And this is the arithmetic mean, to be very precise. Also known as the average. This is a simple average. All of you know how to calculate an average. You sum up all the values and divide it by the count of values to get the average. So this is what mean refers to here in this diagram. So mean, or arithmetic mean to be more precise, is the first one. It is also known as average. Later on, when we deal with probability theory, or if you looked at textbooks of probability, very often this is also referred to as expectation of a variable, often referred to as EX, where X is in parentheses. All right. Before we move on to the next one, just wanted to quickly mention that there are other ways by which you can calculate means. You have geometric means and harmonic means as well. Remember that these two are infrequently used. There are applications, special applications where geometric means and harmonic means are useful, but we'll not be covering that, and it is not that common as the arithmetic mean. The next one that we should definitely talk about is the median. Unlike the mean, which has to do with the value of the parameter or the value of the statistic, the median is a positional thing. So basically, while mean describes value, what median describes is the position. So it's trying to look for, the median is trying to look for the central point by position, not the central point by value. That's an important distinction. Similar to the median, what you have is the first quartile and the third quartile. So what are these really? So what does the median do? Remember that the median is a positional thing. So basically what the median does is picks up the central point of the distribution by position. In effect, it describes the entire distribution into two equal parts. Now the first quartile, what the first quartile is that it further subdivides the lower half of the split given by the median. So the median will give you two parts. Let's say there's a lower part and an upper part. The quartile one further subdivides the lower part into two parts. Similarly, the third quartile further subdivides the upper part into two parts. So in effect, your entire data set is divided into four parts, which has roughly equal number of data points in it. So that is the function of median, first quartile, third quartile. Remember that the median is also referred to as the second quartile. So in effect, you will be seeing the first quartile, second quartile, and the third quartile when you're describing data sets a lot. And since we are describing measures of central tendency, remember that this is not an all-exhaustive list. Another one that you will encounter at times is mode. Mode is nothing but that data point that appears with the highest frequency in a data set is known as mode. Mode can be unique. Mode can also have different or multiple values, depends on the frequency or the repetition of different values in a data set. Mode has applications, especially when you're describing those data sets where the frequency of values becomes far more important or pertinent to the conversation. You'll often find mode being used to also describe geometric curves. So when we say that a distribution is unimodal, what we are saying is that it has one mode or one modal value. There's only one value that appears most frequently. If you say that a distribution is bimodal, what you're saying is that there are two data points that appear with the highest equal frequency. So that equal or close in terms of frequencies would be bimodal data set. Again, these are rather infrequently used in practical applications. So we'll limit ourselves to mean, median, and the quartiles. Now, moving quickly to measures of dispersion, the most common one, and not that useful one at times, is the range. A range has some applications, but in a lot of statistical studies and techniques, you will not encounter range. A range is nothing but, at a very high level, the width of the distributions. You take your maximum and you subtract the minimum from the maximum, so it gives you the range of data values. The next two we can deal with together: standard deviation and variation. Remember that standard deviation, variance. Remember that variance is the square of standard deviation. What do these two refer to? So the standard deviation is nothing but it tries to give a measure of the average distance within the distribution of each data point from the arithmetic mean or from the average value. So it tells us on an average how spread out is the distribution when being measured from the central point of the mean. And the square of that is variance. Some might ask that if you already have standard deviation, then why do you square it and why do you need variance? Sometimes to clearly show the impact of the width of distribution, a variance is better because it's a square value. So remember, the square will grow much faster than the simple variable. That's why variance can often be utilized within statistical methods. It exaggerates the impact of the spread or dispersion of data. Another one that you will encounter is the interquartile range. The interquartile range is nothing but a description of the central 50% of the data. That is a verbal description. Mathematical description of interquartile ranges. It is the difference between the third quartile, and the first quartile. So in effect, what it gives to you is the central 50% of the data points. Sometimes you will also encounter within measures of dispersion, you will also encounter something known as a semi-interquartile, which is the interquartile range divided by 2. And that's another example of measures of dispersion that you will sometimes encounter and look at. Again, not very frequent, but these are the most commonly used ones that you see on the screen right now. So let's take this discussion a bit further. Let's look at the brief mathematical formulation of these. So if you look at a standard mathematics or statistical textbook, what you'll find is that the mean, so here in this, this is the Greek symbol of mu. Mu is often used to describe the mean. And then you will see on the right hand side, you also have an X bar. And that X bar also describes the same thing, which is kind of strange, right? Well, not really. If you remember, we just discussed a while back that if you have access to all the values of the population, then you're talking about a parameter. And if you don't have access to all the values, you're taking a sample of the population and describing the population. Using a sample, you're drawing inferences. So then in that case, that becomes a statistic. So what you see on the left side is basically a parameter or the mean of the population. What you see on the right hand side is the mean of a sample. So the first one is a parameter and the second one is a statistic. What is the importance of this? If in any discussion you see mu referring to mean, remember that this is describing the entire population. If you ever see X bar in the discussion in reference to mean, remember the X bar is not giving you the mean of the entire population. It's only giving you the mean of the sample that has been picked up. All right. So moving on to median. So X squiggly or X tilde can often be used to describe median. Not every textbook follows this notation, but some textbooks do. So in other words, this is the description of median. Remember that while mean or arithmetic mean is a central value, the median is used to refer to the value at a central position. So as you can see here, there are two descriptions of this. One when the count of values is odd and when the count of values is even. So how does this work? So let's say you have a data distribution with 9 data points in it. Since 9 is odd, the central point in that distribution is the 5th data point. Why 5th? Because on either side you have 4 and 4 values each. So that's what this formula tells you. If you were to calculate, so if you have 9 data points, so 9 plus 1 is 10, 10 divided by 2 is 5. So the value at the 5th position is the median in this case when your number of data points is 9. Let's look at another case when the number of data points is even. So let's say if you had 10 data points. In that case, when you have 10 data points, the way to calculate the median in that case is to take the average of the values at the 5th, which is given by n by 2, and the 6th data point. So we look at the values of the 5th and 6th data point and divide it by 2 to get the average. So basically it's the average of the central positional points, the 5th and the 6th point, in case you have 10 data points. So that's what a median is. One important classification here. Remember we had two different notations, one for population, which is mu, and one for sample, which is X bar. You don't have something like that for median. In case of median, it is the same description for both population and sample, and you will simply have to go by the description of the problem or the data set at hand to decipher if this is population or if this is sample. Moving on quickly to quartiles. So quartiles, remember, are extensions of median. The first quartile represents the lower 25%. The third quartile represents the lower 75% of the data set. And that is what is described here by the mathematical formulations. Range is described as nothing but the maximum value minus the minimum value, gives it a total high level width of the distribution. Moving on to standard deviation. Standard deviation, as described earlier on, is nothing but the average distance of each data point in the distribution from the central point of arithmetic mean. As a result, what you'll see is everywhere the individual data point, which is represented by x subscript I, is being subtracted from the parameter average or parameter mean, so that we can get the distance between each point and the mean, and then you square it up, divided by n and under root. N here represents the count of the entire population. So another key thing to remember, there are two different symbols here. If you notice, what you see on the left hand side, sigma represents the standard deviation of a population. As you will see here in the denominator, what you have is the uppercase N, in this case representing the count of the entire population. On the other hand, when you look at the right hand side, on the right hand side, what you'll see is the description is given by S instead of sigma. When you see S mentioned as standard deviation, remember that it is talking about the standard deviation as calculated of the sample, Another key differentiating factor is, if you notice, in the denominator, instead of a uppercase N, you have a small n minus 1. What does this mean? So let's say if you have a population of 100 data points. Out of that, you've picked up a sample of 5 data points only. Now, out of those 5 data points, you are calculating the standard deviation. So when you are substituting the values in the formula, remember that the denominator will become n minus 1, which will be 5 minus 1, or which will be 4. Also remember that while the left hand formula uses distance from mu, the right hand formula is using distance from x bar. Well, no prizes for guessing. Remember that this is a population formula, what you see on the left, and this is a sample formula, what you see on the right. What is the central tendency or the central arithmetic mean? In case of a population, it is represented by mu. What is a central tendency arithmetic mean? For a sample, it's given by x bar. Hence, we see a difference. Some of you might have a question as to why did n or uppercase N become a smaller case n minus 1. Well, the reason for that is that remember that when you're dealing with a sample, in that case, you will have, since you are dealing with a limited number of points, you're likely to get a smaller estimate of standard deviation than is true for the population. And because of that, in order to account for that, the value used in denominator is n minus 1. In other words, a smaller value is used. And remember that when you use a smaller value in denominator, it exaggerates the overall expression or increases the value of the overall expression. So in this case, if you were to use small n and not n minus 1, you'll get a smaller value of standard deviation. But when you use n minus 1, the denominator becomes smaller. As a result, your overall standard deviation increases. So this is a method, like a forced method in statistics, to exaggerate the value of standard deviation so that it more closely represents the actual standard deviation of the population or comes close to it. Remember that as and when your n becomes larger and larger and starts to approach the count of the population, you will get more and more precise values. Moving on, this what you see on the screen right now is nothing but variance. Variance is the square of standard deviation, so it is nothing but the previous expressions have been squared. That's all that this one is. All right, and finally at the end, let's take a look at interquartile range, or IQR. Interquartile range in this case is purely mentioned as nothing but the third quartile minus the first quartile. So in effect, it gives you the mid 50% of data points is your interquartile range. Okay. Moving on from this one, now let's take a look at what this means for us within Excel. So within Excel, the mean for both the population and the sample is calculated by the formula of average. So Excel has an average formula. That's how this is calculated. And remember that what you have on the left side, this is a parameter. Mu is a parameter. X bar is a statistic. Bear the difference in mind. I know I'm repeating this again and again, but it's a very vital and important concept. So hopefully repetition is going to work. X swiggy or X tilde in this case, the swiggly or the tilde in this case refers to the median value. Median has a separate formula within Excel. So if you were to go here and just type in median, as you can see, there is a formula which says returns the median. Similarly, for the formula at the top, what you have is the average. So average, basically, you can simply type in average and you can get the mean or the arithmetic mean of a distribution. So moving on, quartile. So quartile again has a very simple formula. Within Excel, it's quartile, and then you select the list of data points and then specify which quartile do you want. Do you want the first quartile, second quartile, third quartile? Basis that, you then specify QUART, and this will refer you to the quartile value. An example of this is, for instance, let's say you had a set of random values like this, right? And let's say we want to calculate the first quartile of this data set. So we simply put quartile, we select the data set, and if you want the first quartile, you can put the value as 1 and it returns the first quartile. If you want the third quartile, you can put the value as 3 and it will return the third quartile, right? One quick note on this: if you look at the quartile formula within Excel, what you'll notice is, so if I select the data range here, you see what Excel tells you is that the minimum value is 0. So in effect, Excel is giving you the possibility or the choice of 5 quartiles. Those 5 quartiles would be the minimum value, the first quartile, the median, which is also the second quartile, then you have the third quartile, and finally the maximum value, right? So if you were to use 0, for instance, it will give you the number 4, which is the minimum value in this distribution. Very important concept on this. Remember that these 5 values are also referred to as a 5-point summary. So a 5-point summary is one of the ways in which you can describe a data distribution using these 5 values that we just looked at. And we'll also look at a graphical description of a 5-point summary in the second part of the video. But for today, just bear in mind that the quartile formula in Excel gives you access to generate the 5-point summary one by one, but it can give you the 5-point summary of the data distribution, right? You have quartile 1, quartile 3. Range is pretty obvious. We know that we have formulas for max and min within Excel, so we can simply use them. So for instance, let's say I just copy this distribution from here, or rather cut it and paste it here, right? If you have to calculate range of this, so your range will be nothing but the maximum value that you have for this data set minus the minimum value that you have for this data set. So that will give you the range in this case being 5. So that's range. Following this, of course, you have standard deviation. Standard deviation has its own formula. However, in this case, it's important to make an important distinction. So if you look at standard deviation, what you'll find is that there are 2 different formulas for standard deviation and for variance. So on the left side, what you have is standard deviation of the population. So if you're trying to calculate standard deviation of the population, then what you'll use is the stdev.p. And if you're trying to calculate the standard deviation of a sample, which will be a statistic, remember this is a parameter on the left, and what you have on the right is a statistic. If you're trying to calculate the statistic sample deviation, then use .s. So how does this work? So let's say we're trying to calculate the standard deviation on this data set right here. So how would this work? So stdev dot p, and then you select the data set. When you do that, it generates the standard deviation of this as a population. Okay. However, if this was not our population, let's say this was a sample taken from a much larger distribution, then what would be the standard deviation? In that case, the standard deviation would be dot s, and because it's being taken from a sample, then you select it, and once you select it and you run it, you see that the standard deviation is 1.87. Remember, we already discussed this, that the standard deviation of the sample will be a higher value or an inflated or exaggerated value as compared to the standard deviation of the population. And this is on purpose. This is by design. In those cases, when you're dealing with a sample, we know that sample is not going to be the same as the population. It will be a lower value. So that's why it's being exaggerated here as a part of the standard deviation for a sample. All right. Variance works pretty much the same way. You can see the formula is variance.p, and variance.s will help you calculate the variance of this data set right here. So for instance, to calculate the variance of the given data set, if you use var.p for population, and you take the data set right here, it will generate for you the variance of this as a parameter for the entire population. On the other hand, if you were to use variance.s on this, then it will generate that statistic for you, and that statistic is going to be around 3.5, right? Okay, and remember that these are squares of each other, so that 1.71, for instance, if you were to let's say calculate the square root of this value, you will see that you're getting the same value as the value above, right? Why is that? Because remember that variance is square of standard deviation. Again, if I was to take the square root of 3.50, I should be able to, which is the variance in this case of the sample, I should be able to get the variance, the standard deviation of the sample here. So if you just do square root of this, there you are, you have the same value as you got for standard deviation of the sample. Okay. Finally, interquartile range, right? So interquartile range, remember, is going to be a very simple thing. So you basically just do quartile, select the data set. Let's say we do it on the same data set right here. You select the data set, and then right after that you specify that you want the third quartile. And since we are doing the interquartile range, it's the third quartile minus the first quartile. So again, we select the data range and specify 1 in order to generate the first quartile value. And once you subtract them, you can see this is the interquartile range. This is the difference between the third quartile and the first quartile. Okay. All right. Moving on from this to the next one. This is again a simple visual representation. Remember, what you have on the left side is the population. Remember, when you're trying to describe the population, it's called the parameter. The variables are the parameters. So in this case, mu is a parameter for the average, and sigma is a parameter for the standard deviation. Sigma square would be the parameter as in variance for the population. What you have on the right side is purely going to be these, is purely again for sample. In this case, X bar represents a statistic for arithmetic mean, and S represents a statistic for standard deviation. Similarly, if instead of this sample, sample A, if your sample was sample B, then X bar again is the arithmetic mean of this sample, and S is the standard deviation of this sample. Now, for a quick demonstration on this, so let's say we were to generate the mean of this. So in order to generate the mean of this, if we use the formula for, remember, mean is given by average, and then we simply enter all of these data points to generate the mean. So let's take a look at this. Just few more, and there we are. So the mean is 4.33, right? Now let's go ahead and generate the standard deviation of this. The standard deviation of this, since this is a population that you see, is -10, 15, -5, 12, 10, -2, 20, -7, and 6. There we are. So as you can see that in this case, the standard deviation that we're getting is 10.08, right? Now let's go ahead and calculate the mean here. Again, you take the average, and in this case, you have -10, -5, 20, and 6. These are the only four values you have access to. And now let's also generate the standard deviation on this. So in order to generate the standard deviation, what we're going to use is the sample. In this case, you have -10, you have -5, you have 20, and you have 6. Okay, so what you've got here is 13.30, right? That is the standard deviation here. Okay, now let's repeat this exercise for the other data set, but before that, just one quick observation. Remember that the population has 9 data points here. Here also the population has 9 data points, but for the sample we only have 4 data points. Here the population again has 9 data points, and we have more values or more data available to us. So in this case, the sample has 7 data points on it, as you can notice, right? So in this case, let's calculate the mean again. The mean again in this case is going to be the average of all of these values, 12, 10, 20, -7, and 6. So you have the mean. Now let's calculate the standard deviation. In this case, since this is still a sample, this is still not the entire population. You have 10, 5, 12, 10, 20, -7, and 6. Okay, so here you have the standard deviation of 11.24. Perfect. Okay, now for a trick question. The question is, in this case, when we calculated the statistic of x bar a, and we calculated the standard deviation of this, 13.30, is this the standard deviation? So what does this standard deviation represent? Is this the standard deviation of the sample? Not really. This number that you're seeing here right now, 13.30, is an estimate of the population. This is an estimate of the population. This is not the standard deviation of the sample. If you wanted to calculate the sample, if you wanted to calculate the standard deviation of the sample, which means if your sample was itself the population, then you would use stdev.p, because then we are saying that, okay, these 4 data points represent our entire population. But that's not the case here. We are using stdev.s, which means we are telling Excel that these numbers represent a sample. Now, basis the sample, generate for me an estimate of the standard deviation of the entire population. So this is a very important distinction which can sometimes get missed when we are dealing with this. Remember that this number here is not to describe your sample. This number is an estimate of the standard deviation of the entire population of 9 points. All right, the same thing is true here, even though the formula is not any different. But this is again, the moment you write x bar here, you're saying that this is an estimate for the population, estimate that you're generating from the sample. The same thing is true on this side. This number of 11.24 is not the standard deviation of the sample. This is an estimate of the standard deviation of the entire population. Okay. Now, remember that in your first case, in sample A, how many data points do you have? 4. In sample B, how many data points do you have? You have 7 available data points, right? What you will notice is that as the number of data points will increase, both of your mean and your standard deviation start getting closer and closer to the actual population parameter. So if you see here, for the population parameter, your mean was 4.33, right? Now, when you calculated the mean with a sample size of 4, you got 2.75. But when you calculated the mean with a higher sample size of 7, you got 3.71. As you can see, 3.71 is closer to 4.33, right? So as your sample size will increase, your representative statistic will get closer and closer to the actual parameter. Similarly, for standard deviation, if you notice, the actual population parameter standard deviation is 10.08. When we calculated, or rather estimated, the standard deviation of the population, with 4 data points, we got a standard deviation of 13.30, right? But then when we did the same exercise with a larger number of available data points, which is a sample size was 7, you have now got 11.24, which is much more closer to 10.08 than 13.30. Okay, so again, a very crucial thing, or very important observation to keep in mind. Okay, now when we talk about central tendency, remember that you can use the mean, you can use the median. The mean is the central value. Uh, the median is the value of the central position, right? And what you have here right now is you have a data set here all the way from -10 till 25, and what you are able to see here is this is the distribution. You see the blue colored dots on the x-axis. This is the distribution. So if you were to change this, so let's say we change this to -25, you'll see now you have a blue colored dot at -25, right? So this is a distribution. Now, when we calculate the mean of this distribution, so let's go ahead and calculate the mean of this one, right? So there you have the mean value of 0.18, for example, right? So that is going to be the average from C2 till C12 for this value. Okay, so let's go ahead and look at a slightly different number now. So let's say we have -25, and then we have -15, and then we have -25, then you have -15, and then let's put in some other values here. So let's put in fact, let's put in 10. We have 5. Change this to number. And then you have -5, 4, 6, 8, 12. I'm just randomly entering some numbers here. 6, 4, -8, right, and 10. Okay, so what you have is the red colored triangle that you see represents the mean. Okay? The height of the triangle kind of represents the mean in this case, right? Wrong. What we are trying to say is that this difference from 0 till here represents the actual mean, right? The difference from 0, if we were to make an axis, y-axis to here, this is the mean. So this is the value of the mean. Okay. Let's look at the minimum. If you were to look at the minimum of this data set, the minimum will appear. So that blue colored dot represents your minimum of the data set. You can see this is the lowest, right? And then let's look at the quartile as well. So for the quartile, if we just select this data set and select the first quartile, that's our first quartile. Remember that minimum is the lowest. First quartile represents 25%, right? And then after first quartile, let's calculate the median. So median, you can simply calculate median, and there we are. You would then have the median value accordingly on this, right? And apart from the median value, You can use the median function, or what you can also use is you can also use quartile. Remember, median is also known as the second quartile, right? And then let's calculate Q3. Q3 is going to be nothing but this range, and right, this is going to be our next one, which is your quartile here. And then let's calculate the max. The max of this data set is going to be, select this data range, and you have the max, right? So this is how these different values will show up on this. Okay, as you can see that currently we have all of these values, all the way starting from, say, the mean, you have the minimum, you have the quartile 1, you have the median, you have the quartile 3, and the max, right? Now, one important distinction that you might want to bear in mind is that when you're talking about central tendency, remember that central tendency does have units. So for example, if you're trying to measure the average of height, so height in this case is a unit. So if you're measuring height, let's say if you're measuring height in centimeters, when you calculate the average, you will have an average height in centimeters. So you will say that the class has an average height of, let's say, 150 centimeters, for example. Or if you're calculating the weight of a class of students, and you would say that the class has an average weight of 55 kgs, for example, right? Remember that measures of central tendency do have the same units as the units of the base parameter, or the base statistic, or the base variable that you're measuring, right? That's an important thing to bear in mind, this one. Okay, so now just quickly take a look at one more thing. Okay, let's go ahead. That is just a representation, a visual representation of this. Okay, so you have all the points here now, right? Now, another important concept in relation to this is, when we already have mean or arithmetic mean, why do we need the median? Remember that when your data points are roughly normally distributed, then in that case the mean or the average is a very good representation of data. In this case, as you can see, the data points are kind of closely clustered here. So in that case, when the data points are kind of closely clustered, you'll see that the mean is a good representation. The mean kind of lies at the center of this representation here, right? But in those cases where you're dealing with data which is either highly left skewed or right skewed, or you're looking at data which is not normal, in those cases, remember that the median is a much better representation. In fact, oftentimes in the in preliminary statistical analysis, when you're trying to understand the nature of data, if you find at the very onset that the data is normal, you can go with the mean. But if the data is non-normal, then the recommendation that you use the median instead to describe the central tendency of that data set. Okay. And one of the ways that you can understand this is right now, for example, for this cluster of data points, you can see that the red triangle, which represents mean, is a much better representation of the center of this data set, right? Now, as an experiment, let's take a look at what happens when this data set is skewed. Okay, let's take an example of this. Okay, and to show you that example, I'm just going to increase it by 1 decimal point so that you can clearly observe what happens in that case. So what we'll see is, in this case, we're going to get a close cluster of some data points, but then it will be skewed in a certain way. So for instance, and on this one, let's say we have, okay, so now look at this data set right here that you have right now. On this data set, what you have is you have a closely clustered set of data points for all the way from -10 till -5, right? You see all these blue colored dots clustered together. And then you have one data point which is right there at 80, right? In this case, what happens is if you see, the mean has shifted far away from this data cluster. Why? Because the mean is an average, right? That one single large value is skewing the mean. On the other hand, look at the median. The median at minus 7.5 is still relatively much closer to this clustered data set. So what do you think is a better representation for this data set? Is it mean or is it median? The answer is obvious. The median is better placed towards the center of this data set. So in such a case or such scenarios, please rely on the median instead of relying on mean. So that's another very important call out as a part of this. Now, contrary to what you just saw for measures of central tendency, remember that when we are generally discussing dispersion is not tied to those units of measurement, right? Okay. So what I mean to say is that if the lowest weight in the class is, let's say, 40 kgs and the highest weight is 80 kgs, then the range is 40, right? But it's not exactly 40 kilograms because that's just the difference between both of them, right? So now let's take a look at some of this. So let's say I have, or we could technically use the same data points that we have here, just to take a look at this representation. And let's reduce this one as well to 10. So we have a data set here that we're just looking at. Starting off with the simplest one, which is range. So what is range? As you can see, range here is this golden brownish, the golden yellowish colored line. If you look at this data set, what's your lowest data point? Your lowest data point out here is minus 10, right? And what's your highest data point? The highest data point is 10. So what is the range? The range tells you the minimum minus the maximum, as you can see here, right? Also, as you can see that on this skewed data set, if somebody was to say what is the spread of data, while if you look at range, the spread of data seems to be 20 data points. But is that a real practical description of the spread of data? Not really, because you see there's only one data point which is far towards the right, and including the data point actually does not describe the true width of data. And that is why range is very limiting in that sense and oftentimes not very useful for statistical techniques. However, it is still a description of the width, and that's why it's retained. If you take a look at the next one, which is standard deviation as given by the blue colored line, in this case, again, remember that the standard deviation is a much more closer approximation. If you see the width of the data set here, the close clustered green points, the standard deviation is closer to that. And this is a good description of the width of the data set. Finally, the interquartile range. The interquartile range, remember, is the subtraction of Q1 first quartile from Q3, or Q3 minus Q1 gives you the interquartile range. Here in brown color is the interquartile range right here. Okay. And the interquartile range, again, remember, tells you the middle or the central 50% of the data. That's why this is the width of the interquartile range. One important thing here, remember that the positioning of these line segments here on this graph should not be taken, the position should not be taken as any indication. The position by itself has no value here. It is just the width of this line which matters to us. So only the magnitude of this measurement is important to us when we talk about dispersion. It is not where does the segment start and where does the segment end. This is just for visual description. Just go by the length of the line segment. Okay. So this brings us to the end of the visualization for today's video, which is essentially the first part of looking at this. So just a quick recap of this. Remember that we were covering the basics of statistics today as a part of our two-part series. We talked briefly about descriptive statistics and inferential statistics, the difference between what is a population, what is a sample, when do we use both. In addition to that, we also understood what the difference means, at least visually, what could it possibly mean. We covered the fact that when describing a population, you talk a parameter. When describing a sample, in order to estimate the population, use a statistic. Key distinction. Okay. So remember, the statistic is basically when you're using a sample to estimate the population. Okay. Then we talked about the different possible parameters and statistic types. You can measure the central point or the central index of a distribution, or you can measure the spread or the width of the distribution. So you have measures of central tendency, measures of dispersion. Finally, we looked at some of the most common ones that you see on the screen right now. We looked at their mathematical formulations, which is the actual mathematical formula if you were to do this on paper or by hand. Then we looked at the Excel versions of those formulas. We also understood that in some cases, Excel and the way that you write. So one is notationally, there can be a difference. Remember, for example, mu represents the population parameter, while X bar represents the estimate of the population as given by the statistic. So X bar is a statistic, mu is a parameter. Remember that within Excel, sometimes there can be a differentiation of formulas as well, right? So we looked at standard deviation, where dot P means when you're calculating standard deviation of the population. Dot S means that this is going to represent the estimate of the standard deviation of the population from which that sample has been taken. Similarly, for variance, which is the square of standard deviation, var dot P will give you the variance of the population. On the other hand, var dot S will give you the variance, the estimate of the variance of the population from which this sample has been taken, right? Then we just looked at another intuitive concept, which is as and when the size of your sample will increase, you will see that the value of the statistic will become closer and closer to the actual parameter of that population. Following which we just looked at two simple, easy visualizations of this. One important takeaway from this one, I think, was the fact that when you're dealing with highly skewed data, non-normal data, you should go by the median. Remember, the median will be a much better representation when you have non-normal skewed data. On the other hand, if your data is roughly normal or more centrally clustered, it could be normal. It could also be something like a T distribution, for instance. In those cases, you can always use the mean to describe the data set. All right. So that brings us to the end of this video. Hopefully it was informative, and this will help you in getting a better grasp of some of these basics of statistics. So see you next time. Thank you.